Chapter 9 is packed with concepts, ray diagrams and formulas. Let's make light, reflection and refraction simple and exam ready.
Welcome to Teaching Science. Have you ever wondered how light actually works to show us the world? Well, if you're preparing for your CBSE Class 10 board exams, you are in exactly the right place. Today, we're diving deep into Chapter 9, Light, Reflection, and Refraction. We're going to break down every single concept, formula, and diagram step by step in the simplest way possible. No stress, just clear, focused learning. So think about this. You walk into a pitch black room, and you literally can't see a single thing. But the exact second you hit that light switch, bam, everything instantly becomes visible. Have you ever wondered why that happens? Well, during the day, sunlight helps us see, and in that dark room, it's the electric bulb. But the science behind it is actually super fascinating. Basically, an object reflects light that falls on it. When this reflected light travels in straight lines and enters our eyes, that is exactly what enables us to see things. Today, we'll explore exactly how this incredible phenomenon works. Here's our agenda for today. 1. Intro and reflection laws. 2. Spherical mirrors. 3. Mirror formula. 4. Refraction. 5. Lenses and power. And 6. Chapter revision. Section 1. Intro and reflection laws. The foundation of optics. Okay, so whenever light hits a highly polished surface, like a smooth mirror, most of the light just bounces right back. This bouncing back of light into the same medium is what we call reflection. It's literally the reason you can see your beautiful smile in the mirror every morning. Now, what's really interesting are the two absolute rules that reflection always follows. First up, the angle of incidence is always equal to the angle of reflection. Second, the incident ray, the normal, which, by the way, is just an imaginary line drawn perpendicular to the mirror, and the reflected ray all lie in the exact same plane. And, hey, board alert here. Students often think these laws only apply to flat plane mirrors, but actually no. These laws of reflection are applicable to all types of reflecting surfaces, including the curved, spherical ones we're about to look at. Section 2. Spherical Mirrors and Images. Understanding Curved Reflections. Let's move beyond flat mirrors for a second. Have you ever looked at your face in a large, shiny spoon at the dinner table? If you look at the front of the spoon, your face looks kind of different than when you flip it over and look at the back, right? That shiny spoon is actually a perfect real-life example of a curved mirror, and it brilliantly illustrates the two types of spherical mirrors we need to know. On the left, we've got a concave mirror. Notice how the reflecting surface curves inwards, facing towards the center, kind of like a cave. On the right, we have a convex mirror, where the reflecting surface bulges outwards. When parallel light of light hit a concave mirror, they're brought together, or converged, to a single point called the principal focus. But when they hit a convex mirror, the rays spread out, or diverge, and they only appear to come from a focus point behind the mirror. Now, before we start drawing any diagrams, we really need to know a super important mathematical relationship. The distance from the pole of the mirror to the principal focus is the focal length, and we represent that with a small f. The distance to the center of the sphere the mirror was basically cut from is the radius of curvature, or r. For the spherical mirrors we study, the radius of curvature is exactly twice the focal length, so r equals 2f. Here is a quick exam tip for you. If a one-mark question tells you the radius of curvature is 20 centimeters, you can instantly calculate that the focal length is half of that, which is 10 centimeters. Easy, right? So as we move an object closer to a concave mirror, the image actually changes. Here's a simplified chunk of that famous NCERT Table 9.1. Let's break it down so you don't have to just blindly memorize it. Notice the pattern here. When the object is really far away at infinity, the image is tiny, highly diminished, and formed exactly at the focus. As you bring the object closer, say to the center of curvature C, the image moves further away and gets bigger. By the time the object is exactly at C, the image is also at C and is the exact same size as the object. It's like a sliding scale. To actually prove those table values, we use ray diagrams. The most crucial point to remember is this. To find exactly where an image forms, you only ever need to draw two standard rays of light starting from the object. That's it. For example, draw one ray parallel to the principal axis, which will always reflect through the focus. Then draw a second ray passing through the focus, which will always reflect parallel to the axis. The exact point where those two reflected rays intersect, that is where your image is born. Seriously, practice drawing these with a pencil and ruler. It helps so much. Let's apply all this to the real world. Why do you think dentists use concave mirrors? Well, because when they hold it close to your teeth, it creates a highly enlarged image so they can see everything super clearly. Concave mirrors are also used in torches and car headlights to shoot out powerful parallel beams of light. On the flip side, can you guess why cars use convex mirrors for their side rearview mirrors? It's because convex mirrors always form an erect or upright image that is diminished, meaning smaller. This gives the driver a much wider field of view to see all the traffic behind them safely. Pretty smart, right? Section 3. Mirror Formula and Magnification. The Mathematics of Mirrors. I know numericals can sometimes feel a bit intimidating, but I want to reassure you right now. Solving optics numericals is extremely easy if you just follow one simple logical system. And that system is the new Cartesian sign convention. Just imagine your mirror is sitting right on a regular math graph. The pole of the mirror is the center origin, 0, 0. We always place our object on the left side, so light falls from the left. Anything you measure to the right of the mirror is positive, and to the left is negative. Heights pointing up are positive, heights pointing down are negative. Now here is a massive common mistake alert. Students frequently flip their positive and negative signs in the heat of the exam. Just remember your basic x and y axis from math class and you will never get this wrong. Once you have your signs right, you just plug them into the mirror formula box. 1 over v plus 1 over u equals 1 over f. Here, u is simply the object distance, v is the image distance, and f is the focal length. We also have magnification, represented by a small m. This just tells us how much the image is scaled up or down compared to the object. It's the height of the image divided by the height of the object, which mathematically also equals minus v divided by u. Section 4. Refraction of Light. Why light bends. Have you ever noticed a pencil looking totally broken or bent when you place it inside a glass half filled with water? The pencil isn't actually broken, right? It's just playing a trick on your eyes because of the way light behaves when it changes its environment. To understand why, take a look at this enormous number. 300 million meters per second. That is the speed of light in a vacuum. It is literally the fastest thing in the universe. But when light enters a denser medium, like water or a solid glass slab, it actually slows down. This sudden change in speed causes the light ray to bend at the boundary between the two materials. This bending of light is exactly what we call refraction. To measure exactly how much a material slows down light, we use a term called the refractive index. Mark this down, it's an important definition for your board exams. It's simply the ratio of the speed of light in a vacuum to the speed of light in that specific given medium. The higher the refractive index, the denser the material is optically, and the more it's going to slow down and bend that light. Section 5. Lenses and lens power. Refraction in action. So while mirrors reflect light, transparent lenses refract, or bend, light to form images. Just like mirrors, we have two main types. Convex lenses, which are thicker in the middle and act as converging lenses, bringing light rays together, and concave lenses, which are thinner in the middle and act as diverging lenses, spreading light rays apart. Here's a quick look at image formation for a convex lens. Do you notice something familiar about this table? As the object moves closer, the image moves further away and gets larger. Here's an amazing memory trick for you. The image formation rules for a convex lens almost perfectly mirror the behavior of a concave mirror. If you memorize one, you practically know the other. It's a huge time saver. And for solving numericals here, we use the lens formula box. It looks almost identical to the mirror formula, but there is one absolutely critical difference. It's 1 over v minus 1 over u equals 1 over f. I am heavily emphasizing this negative sign. Please make a mental note right now to never confuse the plus sign of the mirror formula with the minus sign of the lens formula during your exams. Our final concept is the power of a lens. Power is basically just how much a lens converges or diverges light, and it's simply the reciprocal of the focal length in meters. P equals 1 over f. Board alert, you will frequently see one-mark questions asking you to define the SI unit of power, which is the diopter. 1 diopter is simply the power of a lens whose focal length is exactly 1 meter. Section 6. Complete chapter revision. 1-minute recap. Wow, congratulations. You have made it through all the core concepts of this incredibly important chapter. You've done amazingly well. Now, let's solidify your learning and lock it into your brain with a rapid-fire revision. I want you to go ahead and take a screenshot of this visual summary card right now. This is your ultimate revision checklist. Remember, light travels in straight lines. For reflection, the angle of incidence equals the angle of reflection. For spherical mirrors, the radius of curvature is twice the focal length. Your mirror formula has a plus sign, your lens formula has a minus sign, and power is 1 over focal length measured in diopters. Review this card before your test and you will absolutely be golden. To really master this chapter, though, you must practice. For your homework, I highly urge you to tackle these important NCERT back exercise questions. Define the principal focus, calculate focal lengths, solve those numericals using the sign conventions, and please, please practice your ray diagrams with a sharp pencil and a proper ruler. Don't just sketch them rough hand. It makes a huge difference. I'm going to leave you with this highly provocative exam question to test your understanding. If you take a convex lens and cover exactly 1/2 of it with black paper, will it still produce a complete image of the object? Think about how those light rays travel. I want you to experiment or think deeply about this and comment your answer down below. If you found this lesson helpful, please like, share, subscribe to Teaching Science, and don't forget to press the bell icon so you never miss our next CBSE Science lesson. Keep studying hard, and I will see you next time.